So, hi. First of all, thanks very much for inviting us for this talk. It's such a pleasure to present our work today here. So I'm Yujin Kwan from Dartmouth College. So today, the study that I'm going to present today touches on one of the long-lasting questions about how the insula represent a wide range of mental processes across pain, emotion, including apparative and aversive processes, and cognitive control. So the insula has been associated with multiple domains of mental function, including pain, to emotion, and to cognitive control, and among many, and also importantly, the integration of these processes. Specifically, one of the influential theories on the functions of the insula argues that the main function of this brain region, especially the anterior portion of it, the anterior insula, is indeed to integrate information across different mental functions such as detecting error, making decisions, paying attention to pain, or processing happy voice. This observation ultimately led to a conclusion that as a result of this functional integration, the insula gives rise to human awareness. However, this theory is in part based on broad claims about overlapping activation across studies with small samples. In contrast to this, recent publications using different neuroscientific techniques portrayed a different picture. So this includes direct brain stimulation study, which you're seeing on the slide right now, where they investigated whether stimulating different parts of the insula leads to different experiences from somatosensory to gustatoolfactory experiences. As you can see, the studies identified more spatially selective representations for these different mental processes. However, direct evidence to test these conflicting claims about the functional selectivity and generalizability across different insula subregions is limited. So this is exactly the study aimed to address with a multi-study data set and Bayes factor framework. So first, specifically, we asked how different insula subregions respond to different mental processes. And then we also asked if the insula, especially the anterior portion of it, does function as an integrative convergence area across different mental functions. So let me start with the data we used to address these questions. So first, I would like to note that this data set was collected thanks to the contribution of our collaborators through a new data sharing initiative, the Affective Neuroimaging Collaboratory, which is open to new collaborators. So this is the structure of our data. So first, we systematically sampled participant-level fMRI contrast maps from 36 studies, focusing on 4 domains of mental process that are widely associated with insula, which is pain, apparative process, aversive process, and cognitive control. This aggregated data set has a balanced structure where each level has equal number of sub-elements. So first, we have 4 domains of mental process at the top. And each domain has 3 subdomains where different experimental manipulations were used, and each subdomain has 3 independent studies. So as an example, the pain domain has 3 subdomains that represent different types of pain experience. That is, pain induced by thermal stimulation, visceral, and mechanical stimulation. And each of these subdomains has 3 independent studies. And this results in 540 participant level images in total. So with this data set, we aim to show the dissociation among these 4 domains across different insula subregions. In other words, we identify which insula subregion represent these domains in a selective or generalizable manner. So in order to do that, here we use Bayes factors which can quantify evidence not only for positive activation, but also for null effect for each domain. And these Bayes factor results, followed by a conjunction analysis, allowed us to identify voxels that are domain selective or domain general. So here, domain selective voxels are defined as voxels that exclusively respond to one of the domains, but not to the others. And domain general voxels are defined as the one that respond to all domains that we included. So here are our results, and let me start with the domain selective regions that we found first. So we found distinct insula subregions that are selectively activated by one of the domains. Specifically, we found a group of voxels in the mid-posterior insula that is selectively activated by pain, and another group of voxels in the mid-insula that exclusively respond to apparative process, and in the anterior-ventral insula by aversive process, and lastly, in the anterior and mid-dorsal insula by cognitive control. Then we checked these selectivity patterns by looking at their activation profiles for each domain. In the interest of time, let me focus on the pain-selective regions here. So here we can see the pain-selective region indeed show a higher activation for pain compared to the other domains. We also checked their spatial correlation with the topic maps registered on Neuroscience, an automated meta-analysis tool based on 14,000 previous neuroimaging studies. With this method, we can see which keywords has been highly associated with the region of interest based on previous findings. So let me also zoom in on the pain-selected region again. So here we can also observe specifically pain-related topics appear as the most highly correlated words with this area. And overall, we were able to see the same patterns in the other domain-selected regions in terms of their activation profiles and spatial correlation with the Neuroscience topic maps. And we also found a domain general area. And we found this region in the anterior insula, but in a more specific location than previously reported, that engages across all 4 domains that we included and potentially integrates information from other insula subregions. And this region shows very different patterns compared to the domain-selective area that I just introduced. So first of all, as you can see, this region shows overall activation for all 4 domains of mental process. And also we can see that the neuroscience topics that show the highest correlation with this area are much less coherent compared to the other selective regions. Based on this result, currently we are looking into other neuroscientific evidence that can provide more clues about the functions of these regions, including neurotransmitter receptor profile, structural and functional connectivity, cytoarchitecture, other existing meta-analysis. Lastly, among these results, I will briefly go over some of the preliminary results of one of these directions, neurotransmitter receptor profile. So here we are using a comprehensive atlas of neurotransmitter receptors that recently came out by Hansen and her colleague. And this atlas includes 9 neurotransmitter systems, 19 receptors and transporters from 36 PET studies, including 1,200 participants. And with this atlas, we are investigating if the domain-selective and domain-general regions from our study have distinct neurotransmitter receptor profile compared to each other. And we did this by calculating spatial similarity between the 5 regions in our study and this neurotransmitter receptor atlas. So here, a higher similarity would indicate a higher density of a given neurotransmitter receptor in a given region. So our preliminary results show quite distinct patterns across the 5 regions in our study. In the interest of time, again, let me focus on the pain-selective region here. So what you are seeing here is a polar plot where each point in the circle corresponds to one of the 36 studies in the atlas, and the distance between the center and the red line indicates a degree of similarity between the given neurotransmitter receptor map and the pain-selective region in our study. In other words, the density of the given neurotransmitter receptor in this area. So here we can see the pain-selective regions show high similarity or high density of the neurotransmitters that have been known to play an important role in pain transmission and modulation, such as glutamate, GABA, and cannabinoid, and opioid. So even though further analysis are still in progress, but we think they are already quite hypothesis generating, given that they are well aligned with previous individual findings of the function of these neurotransmitters on various aspects of pain processing, and therefore have a lots of potential to provide critical evidence to the neurochemical characteristics and functions of each domain-selective and domain-general regions in our study. So as a conclusion, in this study, we identify specific subregions in the insula that are selected for or generalizable across 4 domains of mental function using a combination of full voxel level maps in a large sample and Bayesian evidence in support of null effects. And we also confirmed that this domain-selective and domain-general region that we found show distinct activation profile, spatial correlation patterns with neuroscience topic maps, and neurotransmitter receptor profiles. And together, our results provide direct evidence for a high degree of domain selectivity in the insula, but also found a specific area in the anterior insula that supports for the theories of integrative function. So for more discussion and results, please visit us at our poster during our second presentation session tomorrow between 2 to 3 p.m. The poster number is MT450. And on that note, I would like to thank our collaborators who made this study possible by providing and sharing their data and feedback on our results through Affective Neuroimaging Collaboratory. And also, I would like to thank my other co-authors and my lab members for their support and collaboration. And thank you for your attention.
Thank you very much. We have questions that have been voted 7 times here. It is the following. Is there any hemispheric lateralization in the function of the insula?
There was. We didn't really focus on in the reporting the result today, but for example, if I focus on the pain selective region again, we definitely have a bigger and higher activation for pain selectivity in the right hemisphere. And I expect we could find lateralization for the other 3 domains that we include in our study. We can definitely look into that.
Thank you.
Okay, we're going to move to our next speaker, and that is Julia Fitz from the Max Planck Institute of Psychiatry in Germany. And so she's just going to set up her laptop, and we will get going.
Just as a reminder, if you have any questions, you can use the web app directly and ask your question on the app, and the most voted question will be asked.
And if 2 OHBM chairs can figure it out, you probably can figure it out better than us.
I'll take it. Okay.
Okay, so everything is set up now, and so I'm Julia Fitz from Munich, from the Max Planck Institute of Psychiatry, and I will talk about simultaneous fMRI and pupillometry during a cognitive task which reveals affective processing. So first of all, as we're in the field of psychiatry, the current nosology systems of mental disorders, such as the DSM-5 or the ICD-10 or 11, face multiple challenges, as diagnostic criteria are heterogeneous and show considerable overlap. For example, the majority of individuals fulfill the criteria for more than one diagnosis within anxiety and mood disorders and many more. This heterogeneity is not only evident on the symptom level, but also in the underlying behavior and physiology, which is impeding the understanding of disease mechanisms and identification of biomarkers. And to address this issue within and between diagnostic categories, it is essential to study transdiagnostic samples, focusing on constructs that span numerous disorders in order to foster the data-driven discovery of endophenotypes and potential treatment targets. And actually, cognitive systems constitute such a transdiagnostic risk factor, as dysfunctions are present across psychopathology and are associated with the burden of disease. So in this study, our goal was to integrate multiple levels of assessment, and the basis for our analysis was the NBAC task. And the NBAC is assessing working memory quite reliably, especially in the fMRI. And participants need to indicate whether a certain letter matches the letter and steps before. And we used the pupil, which is sensitive to cognitive demand or working memory load. And we also had data on the brain functionality and independent neurocognitive assessment, as well as measurements on anxiety and depression symptoms. And pupil and fMRI during the NBAC task were recorded simultaneously. So what was our question? What did we try to answer with this setup? So we tried to address whether pupillometry can generate valid biomarkers for cognitive dysfunction. And we believe that physiological parameters of cognitive processing could provide a more in-depth understanding of the brain-behavior relationship and therefore facilitate also the identification of biomarkers. The sample we used is a transdiagnostic sample, so it spans from healthy controls to disease. And the diseases we're talking about, there are anxiety and affective disorders, PTSD, OCD, and several other comorbidities. So it's not a clear-cut sample, it's just how the reality looks like. And the sample is the BECOME cohort, which is an in-house study at the Max Planck Institute in Munich. So in total, we used for this analysis 226 participants, which were recruited until our fixed date. And the study is still ongoing. So here we have an overview of the methods, and I will guide you through it. So we used the pupil data, related to our research question, and we used individual mean pupil sizes within each condition of the NBAC task, and put it into the latent class growth modeling. So this is a technique which is a data-driven modeling technique which detects heterogeneity in time series data. So we have our time series with these different working memory conditions. It clusters groups of individuals based on their growth trajectories, which are defined by growth parameters such as intercept and slope. Then we selected the best fitting model based on the Bayesian information criterion. In the next step, we validated it based on randomly selecting subsamples of our total sample. Then in the step 3, we calculated individual pupil profile scores, which I explain more in the next slide because it's more understandable. In a subsequent step, we analyzed associations between this individual pupil profile score and neurocognitive functioning and the symptom levels of depression and anxiety, while controlling for sex, age, and years of education. And in our final step, we tried to biologically validate our clusters and looked into the correlation of our pupil profiles and the fMRI during the bold signal during the NBAC task. Okay, so here, before we go into the result, just a quick explanation. So what we see here on the y-axis is the pupil size within all the conditions, which you see on the x-axis. And the typical profile, which we would expect, would be a stepwise increase. So the lowest pupil size in fixation to the largest pupil size in 2-back. And through the modeling technique, the latent class growth modeling, which we used, we could actually detect 2 different clusters which were robust. So we have the large cluster with the stepwise increase, which you would actually expect, and then we have the non-reactive cluster where there is no increase in the low levels and only a slightly increase in the higher level of working memory load. And the IPP, or the individual pupil profile score, which we generated, is basically that we subtracted the fixation condition from the one-back condition, because as you can see on the plot, this is the biggest differentiation between those two groups. Okay, so now about the results. So we associated the IPP, or the individual pupil profile score, with the behavior of the NBAC task. And we could see that the pupil profile score is related to reaction time in the zero-back condition and reaction time, like normally significant to the two-back condition. And results indicated with the asterisk means that they survive Bonferroni correction. And there were no significant results associated with accuracy rates in the NBAC task. And here we use the IPP, or the individual pupil profile score, with the independent neurocognitive assessment. And we see strong results with cognitive flexibility and selective attention. And in both these slides with the result groups I just showed, is that people with a stronger increase in the pupil, they perform better on these tests. And interestingly, we also looked into the linguistic domains, such as verbal memory and crystallized intelligence and word fluency, and there were no significant results, as well as depression and anxiety symptoms were not related to the IPP. Okay, and now the fMRI results. So what we did is that we used the pupil size group mean values and added them as a parametric modulation into the model. And here what we see is the correlation of the group mean pupil size with the bold signal in both groups separately. And what we see is that this pupil size is correlated with the frontoparietal network and some parts of the Salience network, such as the insula. And here, the interesting result is that we also looked at the differential contrast, which showed more positive correlations of pupil size in the frontoparietal network in the non-reactive group compared to the reactive group. And this was accompanied by more negative correlations in the deactivated regions in the non-reactive group, such as the amygdala, anterior cingulate gyrus, hippocampus, nucleus accumbens, ventral tegmental area, and posterior cingulate. And interestingly, the thalamus showed activation positively correlated with pupil size in the reactive group and deactivation in the non-reactive group. So the contrast estimates are also visible, like some of the contrast estimates are also visible on the bottom of the slide. So to conclude, so first of all, we were able to identify individual pupil response profiles during a working memory task. And we identified two distinct profiles, one reactive and one non-reactive. And we could conclude that this is related to neurocognitive functioning in processing speed and executive functioning, not in linguistic domains. And we conclude that this pupil size acts as a proxy for, on the one side, for cognitive effort, but also on the other side, as a proxy for arousal. And this is something what we see in the fMRI and the pupil and fMRI bold coupling, as there are stronger deactivations in the default mode network and paralimbic regions and stronger activations in the frontoparietal network in the non-reactive group, despite decreased neurocognitive performance. And in a follow-up analysis, we also looked into how the acuteness of psychopathology actually modulates these results. And this is something we are about now to write into the paper. So this doesn't had any more room here for this. But if you're interested, you can always approach me. And here I would like to thank you for your attention and for all my supervisors and group members. So.
Thank you very much. So we have a question. Do you think measuring the standard deviation to to measure the dynamic of the...
Sorry, I can't hear.
Do you think measuring the standard deviation to measure the dynamic of the change of the pupil rather than the mean size of the pupil will be a better indicator of the cognitive demand?
Yeah, interesting question. So last year we published a paper on this. So it was in a healthy control sample, and we used on one hand the mean pupil size per condition as we did here, and the not standard deviation, but we called it the within condition fluctuation. So we used the first order derivative, and we could strongly see that with the pupil size we have the main focus on frontoparietal networks and some in a salience network, and with the pupil change, that's what we called it, we see clearly the salience network. And this is how we extracted two different processes. But in this study, we're focusing on this more, we tried to focus more on this cognitive part, and that's why we related to the pupil size itself. And yeah, so these fluctuations are also interesting and could be also worth looking into. But yeah, yeah. But if you're interested in, you can read this paper. It's published in Human Brain Mapping.
Thank you, Julia. And we're being brutal on time because people have other commitments, and I just want to keep people to time so people can get to other commitments and see the talks they'd like. So we are now, we're going to have Ben Dean's presentation and he's at the Rockefeller University. And he is not here with us today, so we're going to look at the video. So we have our audio-visual help here, very efficient. So, but let's give Julia a round of applause. Thank you.
Hi, my name is Ben Dean. I'm a postdoc in the Freiwald lab at the Rockefeller University. Today I'll be talking about systems for social and spatial reasoning in the human brain. So I'm interested in how we understand other people, their behavior, and their internal mental states. Prior neuroimaging research has identified a set of brain regions across the frontal, temporal, and parietal lobes that reliably respond strongly when we think about other people relative to a range of control conditions. These areas fall within broad zones of cortex, referred to as the default mode network or apex network, which have been argued to be anatomically positioned at the top or apex of a rough hierarchy of anatomical connectivity in cortex. Across a range of studies and separate groups of participants, these broad zones of cortex have been implicated also in a range of other functions, including semantic and episodic memory, spatial cognition, and reward-based decision-making. So today I want to ask what we should make of social responses within the default mode network, given this range of other functional responses that have been observed. I'm going to introduce a novel theoretical framework that describes parallel but content-specific subnetworks within the apex network, and then I'll test some basic predictions of this theoretical framework using a human fMRI study. Understanding other people has been argued to rely on an internal model of how others' mental states, like beliefs, emotions, and desires, give rise to their behavior. This is known as the theory of mind. To understand specific familiar people's behavior, we have to conjoin this abstract structure with representations of specific people and their specific mental states. Likewise, in the spatial domain, our ability to understand and navigate other places has been argued to rely on internal models of Euclidean distance relationships between locations in space. These are known as cognitive maps or graphs. And to understand specific familiar places, these abstract relationships must be conjoined with content from experience about what is where in an environment. So these processes are arguably in some sense parallel at the cognitive level. And I'll argue here that they're also parallel in their neural implementation. Specifically, that parallel subnetworks within the default mode network support these internal generative models for familiar people and places, and that these networks include components with direct interactions with the hippocampal formation that support the building of models of specific familiar people and places based on information from experience. These internal models can in turn be used to support a range of processes that have been classically treated as distinct. This includes structuring semantic and episodic memories, reasoning and decision-making about events occurring in the present, and predicting and simulating events in the future. I'll test some basic predictions of this theoretical framework in a human fMRI study using precision fMRI within individual subjects scanned multiple times, 3 times for a total of 7.5 hours across a range of perceptual and cognitive tasks. We used optimized data acquisition and analysis methods, including multi-echo pulse sequences and optimized pre-processing methods in order to maximize temporal signal-to-noise ratio while minimizing spatial blurring. We used 4 tasks. First, a visual perception task, in which participants viewed images of familiar and unfamiliar people and places, as well as generic objects. A semantic judgment task, in which participants rated personality traits of familiar people, physical properties of familiar objects, and spatial or navigational properties of familiar places. An episodic task, in which participants imagined events involving familiar people and places or objects. And lastly, a theory of mind's localizer, which participants read brief stories and answered true or false questions, either about characters' mental states or physical states of the world. First, test the prediction that parallel responses within the Apex network exist in response to people and places. So here I'm showing a comparison of people and places in the episodic task for a representative individual participant. This is what we see within medial prefrontal cortex. We see a pattern of alternating responses to people, places, and people. Within medial parietal cortex, we see a similar pattern of alternation in response to people, places, and places. In the temporoparietal junction, we see a pair of regions, one of which responds to people, one to places. And in the superior frontal gyrus, we again see a pattern of alternation. These responses are consistent across the semantic task as well as the visual task, arguing for parallel parts of the default mode network responsive to people and places. We next test the hypothesis that these sets of regions include zones of cortex with known anatomical connections to the hippocampal formation. So in response to people, we see a region of the temporal pole, a primate-specific brain region with direct bidirectional connections to entorhinal cortex in primates. This response is consistent across all of the subjects in our study and all 3 tasks. And in the spatial domain, we see responses within retrosplenial cortex and perihippocampal cortex, areas with established anatomical connectivity with the hippocampal formation, both in rodents and primates, via entorhinal cortex and the subicular formation. So these results indicate that these sets of areas include interfaces with the hippocampus. Next, we test the hypothesis that these regions respond specifically to their preferred category. We do so using an ROI analysis, in which we define functional regions of interest as the top 5% of person or place preferring coordinates within anatomical search spaces, capturing zones of the default mode network. We then extract responses across all conditions in the study in left-out data. So here I'm showing responses in person preferring regions of the medial parietal cortex. In the visual task, this area responds much more strongly to familiar people than unfamiliar people, as well as both types of places and objects. We see a consistent response to people over objects and places in the semantic task and the episodic task, as well as a response to mental over physical reasoning in the theory of mind's localizer. These results were consistent across all of the person preferring areas we observed, despite their divergence in specific anatomical location. These results indicate a response profile that's best explained by content domain and can't be explained by a compound specific to any one of the tasks. Complementarily, we see in place-preferring regions a response that's specific to familiar places, again across visual, semantic, and episodic tasks, and no response in the theory of mind's localizer. So these results demonstrate that these responses are domain-specific and not just domain-preferring. Lastly, we test the prediction that these sets of areas form functionally coupled networks by assessing resting state correlations between these ROIs. Here I'm showing a correlation matrix between all of the ROIs that I just described, and we see strong correlations within parts of the apex network that have similar category preferences to regions that prefer people or places, but weak or zero correlation between those two sets of areas. Here I'm showing a quantitative analysis of this effect, and this demonstrates that these sets of regions can be thought of as functionally coupled networks and two parallel distinct functionally coupled networks. So these results demonstrate that within the cortical apex, parts of cortex considered to be at the top of an anatomical hierarchy, we see strong domain specificity and specifically parallel networks that respond to familiar people and familiar places, including nodes with known anatomical connections to the hippocampal formation. We argue that these results support our theoretical framework and are consistent with the idea that these networks support internal generative models of people and places. This framework provides a parsimonious explanation of the responses that we observe to people and places across tasks with rather different sort of specific information content and cognitive processing, including visual, semantic, and episodic tasks. All right, so I want to thank you all for listening, my advisor, Vinrik Freiwald, and our funding sources. And if you're interested in exploring this work further, you can check out our preprints, which is up on bioRxiv. Thanks.
Okay, so that was a very nice presentation from Dr. Dean. I hope everyone could hear and see that well. And so now we're going to, we would have had Hong Wen Song from the University of Science and Technology of China, but they have not made it here, unfortunately. And so we're going to just fill in a little bit of a block of time because we want to stay to time so people can join from other sessions. And Michelle and I were just wondering about what you felt about studying the embodied brain in social neuroscience in the 21st century, and how you feel about the role of EXG signals, signals such as we've seen pupillometry here with signals such as muscle activity, gut activity, other kinds of signals, galvanic skin response and so on, in addition to the functional assessments that we usually do using fMRI, MEG, EEG and FNEAS and so on. And so we just wanted to have a little bit of a discussion about that. And for that, we've got microphones here that are in the audience. So we welcome your comments and what you think.
Also, you can use the app directly.
And you can use the app too to type if you would feel more comfortable, because some people don't feel comfortable speaking in a microphone. So what do you think? Are we doing enough in social neuroscience the way we're doing our studies now, or do we need to do more? I'm trying to provoke a reaction here. All right, Professor Thibault de Schotten, what do you think of this issue?
I think we can always do more. The question is, what can we do? I didn't see so much electrodermal measurement.
Yeah, it's difficult to do, particularly in a fMRI environment, and many people do that. And we are actually wrestling with that in our lab at the moment. We have a EEG set up, and so we're trying to do other modalities, and it's challenging. It's challenging to set up subjects. It's time intensive, but it can tell us about other. There's functional. There are going to be functional relationships between bodily signals and bodily feedback and interoceptive feedback that will modify one's cognitive or other sorts of behaviours. And so I personally think that it's a very important thing to do, to model and include these responses in the models. So.
We have a comment
Okay,
that is going in that direction. Somebody said, personally, I have enough work on my hands with the measurement I have. Basic physiology should definitely be measured. So.
Yeah, it is. It's tough, isn't it, to do that physiology, and it's really and some of these methods are invasive. Not invasive in terms of invading the body boundary, but certainly in terms of studying the subjects. You know, if you want to do an electrogastrogram and look at, you know, the brain-gut axis or the brain-heart axis, you have to put electrodes on the torso. And so that can have many issues for setting up subjects, privacy issues, and you know, some subjects who have who come from different religious faiths may not appreciate having, you know, things put on their body or even on their heads. So there are these other kinds of issues that we have to be sensitive to when we study subjects. But it is a lot of work, I agree.
We do have another hit comment. It is, for being called social, we aren't really taking into account what being social means, when most scientists don't take into account gender, culture, and SES.
Yeah, absolutely right. And we need to be doing that and putting that into our models. That's a very, very important comment. And also, that comment came up, a similar comment came up this morning in the keynote about studying white subjects. And so we need much, much more diversity in our subject population. And that's really, really important because there are going to be differences potentially. So that's a really good point.
Another point was regarding improving the application of virtual reality tasks in fMRI.
Oh, sorry?
Implementing virtual reality tasks in fMRI.
Yeah, that is certainly very important. Virtual reality and actually what's really interesting right now, we can also, with virtual reality, is certainly very, very important, but with these portable systems, with portable EEG, optically pumped magnetometers, still not quite portable yet, there's much more scope for perhaps linking the 3D environment that we are experiencing now in real life with studies of virtual reality, where, you know, you're looking at stimuli that are synthetic and the display is the two-dimensional one. And that's a really important area to try and bridge the gap between real-life studies and studies that we do in the lab. So that's a good point.
Another point was regarding the use of functional near-infrared spectroscopies that could be really helpful to measure social dimension.
Yeah, and of course we've got someone at the mic. I was just going to add that there we can add EEG electrodes on there and measure both at the same time. And you wanted to make a point at the microphone, number 4, please.
Oh, you can't hear me. Going back to the question of like how we define social, this is something my lab mates and I were discussing earlier this morning. You think about how we can say social is like interacting with other people, but it's becoming more and more common to to treat inanimate objects as people. I can't say the word.
Yes.
And so, you know, do we consider that social, or considering interaction with animals social, like if you talk to your pets or something like that? And I think that's something that I don't know if we've necessarily thought about that in the context of our work and how that would affect experiments moving forward.
Yeah, that's a good point. I haven't really, there have been some studies but they're very small about pet owners, and particularly mainly with dogs, and looking at how dogs respond to the gaze of the owner and social attention. And they are better at gaze change detection than, say, pointing behaviours. They just won't respond to that. So there is some literature on that. But yeah, that's important because that is a interaction with another sentient being, isn't it? And that's something that is neglected.
Yeah.
So that's a really good point. I'm glad you mentioned that.
Yeah, even if we're not communicating verbally, like using verbal language, body language is another thing that might come into play there as well.
Totally. I studied nonverbal communication. That's music to my ears. Yeah. Thank you for that comment. Yeah.
Another comment was that it'll be important not to fall into the trap of using physiological response as an explicit criterion for affective experience. Like you can have no SCR and still have a fear experience.
Yeah, that's an interesting thing about these affective experiences, and it touches on, and that touches a lot of deep issues about what emotions are, because there's a big debate about emotions and also autonomic changes that seed those percepts and influence our cognition. And they can do it also at a level that's not amenable to our awareness. And so it's a really complex area, and it's really hard to disentangle. And so that was when I asked you guys that question about these EXG signals. That's what I was kind of getting at, and what was in the back of my mind, because there's a big variance bucket. People study cognition, but there's a very big variance bucket. Now it contains emotion, it contains autonomic system kind of variability, and we need to be kind of dipping into that bucket and trying to empty it out, and I think we'd be understanding the brain a bit better. So that was thank you for those comments online, and thank you for coming up to the microphone, and hopefully that'll seed people's ideas for future experiments, because that's what we need right now. We need ecologically valid and realistic experimentation. And so we are now at time for our next presentation, and that would be a video, and it's by Giada Letteri, and from the University of Louvain in Belgium. And then we will have one more presenter after that, and he's here, so don't go away. So we'll hear Giada Letteri's video now.
Hello everyone, I'm Giada and I'm honored to be here to present one of my latest work that investigated the representation of affect in sensory deprived individuals using different sensory modalities. And first of all, I just want to quickly remind you the importance of emotions and affect in our daily life, as we are constantly immersed in a social dynamic environment where emotional signals coming from ourselves and other individuals are typically conveyed through different sensory modalities, but mainly through vision and audition, as for instance, emotional facial expressions and spoken communication like shouting or other type of utterances. And nevertheless, so far it has often been considered a modality-independent representation of affect, so it is actually unknown how the lack of sensory experience can modulate, and if modulate, how the brain represents emotional experiences. So therefore, what we aim to do in our work was to investigate exactly how the brain represents affective experiences in different sensory modalities and in individuals that are lacking sensory experience from birth. And to do so, we employed a movie for our naturalistic simulation, and in details we presented to sighted and normally hearing individuals an audiovisual, an audio-only and a video-only version of the 101 Dalmatians live-action movie, and we asked them to provide a continuous rating of their emotional experience during the movie. So they were using a keyboard to indicate for 15 different emotion categories their presence during the watching or the listening of the movie. And the word cloud represent here the categories that were available to participants, and the size is proportional to their use during the experiment. In here, you can observe an example of the emotion data that we collected. So in the first picture is the emotional trace for one participant attending the audio-only modality of the movie, and in black, the points in which the emotion was present, and the same for audio-video in the second figure. In the third one, we have the group average rating, where the darkest color represents the point of maximum agreement across subjects in emotional ratings. The matrices in the bottom part of the slide represent the dissimilarity between emotion ratings within condition, which we then correlated and assessed, so the correlation in the structure of affective responses across condition. And we can observe that there is a strong association between modalities, so overall they all evoked the same type of emotional response. Starting from group level emotion ratings, we ran PCA and extracted the first component, which was valence. Then, for the fMRI experiment, we asked a group of sighted individuals, a group of congenitally blind and a group of congenitally deaf, to enjoy the same versions of the movie that we employed in the behavioral experiment. So they were not asked to perform any kind of task, but simply attend to the movie in the modality through which it was presented. Then we employed voxel-wise encoding to measure the association between brain activity and emotional experience. So we started from our matrix time points per emotion for each condition, and we convolved it with a canonical hemodynamic response function, and then we fitted it with the brain activity of the groups that attended the condition. So for instance, we used the behavioral ratings obtained from the audio-only modality and fitted it in the activity of congenitally blind individuals attending the same version. We then obtained the R-squared for the full model, and we built a null distribution of R-squared through 1,000 null encoding matrices. We then repeated this procedure for each subject, and to obtain group level results, we averaged the effect and null distribution using a non-parametric combination approach we then corrected for multiple comparisons. And this procedure gives us a map of regions significantly encoding the affective experience in each modality. So we just repeated this procedure for all conditions. And with the group level results, we performed two conjunction analyses to highlight regions significantly encoding emotions regardless of sensory modality and experience. Then we used MVPA to cross-decode the valence reported in different conditions, so the three modalities in which the movie was presented. And we started from the logical OR map of the brain regions highlighted by the voxel-wise encoding procedure. So to estimate the association between valence and brain activity in each group, we did a k-fold procedure, and to estimate the best lambda value for our cross-decoding. So in the figure, you can see an example for the audio-video condition that was used as our training test. So we performed the cross-validated regression with the dependent variable being valence, and we obtained the penalized regression coefficients to use in our test set, which were all the other conditions other than the audio-video one. Then we used the root mean square error as our metric to measure how much our prediction is close to the observed value, and we created 10,000 null distributions from our prediction, which was then shuffled and computed again. So by doing this, so training on each condition or group and testing on all the other conditions or groups, so we were able to build a matrix of cross-decoding, which we then corrected again with the FDR measure to observe then which group and modalities could be predicted from the others. So going to the results, here we show the results for the voxel-wise encoding procedure per sensory modality, so audio, video, audio, and video only. We can observe some regions showing modality-specific behavior, like the visual cortex in the video-only condition, but more interestingly, we can also observe other regions which tracks the emotional experience depending on the sensory modality through which the stimulus is conveyed, as STG and ventromedial prefrontal cortex. And this finding is well highlighted by the results of our conjunction analysis, which in this case shows in white the regions significantly present across the modalities. So as we said, mainly ventromedial prefrontal cortex and superior temporal gyrus. Here are instead the results for the voxel-wise encoding procedure per sensory experience, so with a group of normally hearing and sighted and congenitally blinds and deafs. And again, some regions are engaged regardless of the sensory experience, and we also found that the affective experience during the movie is encoded in occipital cortices in blind individuals. So this might suggest a reorganization of this area in case of sensory deprivation. And here again, results from the conjunction analysis will highlight the involvement of specific regions as ventromedial prefrontal cortex and the superior temporal gyrus across sensory experience of participants. And then, by pulling together results from all modalities and groups, it is even more clear the role of these two regions. So we used this set of areas to perform the MVPA cross-decoding. And here are the results for the cross-decoding procedure. And so from the obtained matrix, we can observe how we are able to successfully train using blind participants and decode all other groups and modalities. While for not deprived individuals, we can train using the audio-video modality and the video modality only. And by using them, we are able to decode significantly all other conditions and groups except the audio modality in the control group. While for the group of auditory deprived individuals, we can train on them and decode both the audio-video and video modality of controls, but again, not the audio one. Indeed, by using the audio modality of controls, we could not decode any other group or modality. So it might be that this modality is actually less common for normally hearing and sighted participants, so it shows a deviant behavior. In the bottom part of the figure, instead, we reported the average training coefficients in all conditions and groups that were significant in the test, so all of them except the audio modality. And we can see in basically the relationship so that to a negative beta corresponds a higher valence and the opposite. So we can observe how in ventromedial prefrontal cortex we have an anteroposterior pattern, while STS has negative coefficients and the occipital lobe positive ones. So this gives us also more information about the real relationship between the brain activity and the emotional experience during the movie. And so, to conclude, we found that two regions are actually involved in the emotional experience, regardless of the sensory modality through which this is conveyed, and also independently from the sensory experience of individuals. And interestingly, we also found that in congenitally sight-deprived subjects, the occipital cortex has a role in the emotional trace. So this suggests a reorganization of this area. And moreover, we can actually discuss a cross-modal reorganization of affect in blindness, since we were able to cross-decode all other groups and conditions by starting from the trace obtained from blind participants listening to the audio movie, while the same could not happen when we used sighted participants exposed to the audio-only modality. So that's why we suggest a cross-modal reorganization of affect in the condition of sensory deprived individuals. And with this, I conclude, and I thank the people involved in the work, especially my former supervisor, Luca Cecchetti, and you for your attention. And I really hope to see you in person. Thank you.
Okay, we come to the last presenter of our session today, and that is Martin Gell from RWTH, Aachen University in Germany. And give him a round of applause. And he's just going to set his computer up, and then we'll get going. And again, it'd be great if you can ask some questions. While he's getting ready, you can be looking at the abstract.
Okay, thank you. All right. Okay, so hello everyone. My name is Martin Gell, and I would like to tell you about my poster where we explored the functional networks underlying impulsivity. Okay, so just to get everyone on the same page, impulsivity can be defined. Ooh. Oh, use laptop. All right. Okay, sorry about that. So impulsivity can be defined as behavior without adequate foresight, or otherwise a tendency towards actions without disregarding their consequences. Many have argued for this to be a multidimensional construct, spanning diverse behaviors from response inhibition to delay and reward sensitivity. To this date, neuroimaging studies have not really tackled this dimensional nature of impulsivity, making the investigation of common and independent neurocorrelates difficult. So what we aim to do here was to delineate a comprehensive network that's associated with impulsive behavior, spanning two of these dimensions, that being delay consequence sensitivity and response inhibition. We then also sought to characterize this network's organization and its chemical properties, but about that in a minute. So first we did an LLE coordinate-based meta-analysis of studies that contrast impulsive and controlled processes. What exactly do I mean by this? Well, let's take the example of delay consequence sensitivity, which is here studied using delay discounting tasks. So here we take studies that contrast smaller choices of smaller sooner rewards with choices of larger later rewards. Here the choices of smaller sooner rewards reflect an impulsive act, while the choices of larger later reward here would reflect a controlled act. Here we take also the opposite contrast, as well as subjective value, because the way subjects value these rewards that they are looking at, it affects these contrasts. For response inhibition, this is studied using the stop signal and go no-go task, and here again we take studies that contrast error, such as inhibition failure, and successful inhibition. Again, here this reflects the impulsive versus the controlled act, as well as the vice versa contrast. Okay, so what have we found? Well, first of all, we found no convergence for the contrast of controlled versus impulsive behavior. For the opposite contrast, here the impulsive versus the controlled behavior, as well as the subjective value, we actually find a very similar network of regions, mostly located in the ventromedial prefrontal cortex, as well as the ventral striatum. For response inhibition, for the controlled versus impulsive acts, here we find, where you can see in blue, a network, a right lateralized network of frontoparietal regions. And in the red you can see the opposite contrast of the impulsive versus the controlled acts, which results in, well, converges mostly in the middle cingulate areas as well as the superior frontal gyrus. I would also note that on the right here you see that these two contrasts also have a substantial amount of overlap, mostly in the anterior insula and supramarginal gyrus. Okay, so to kind of conclude the meta-analytical results, we find two non-overlapping meta-analytical networks, one centered in medial default mode network, that being the one related to delay consequence sensitivity, those are the nodes in the blue, which has been mostly associated with goal-directed decision-making. And the red network of regions appears to be distributed over higher order networks associated with executive function. Okay, so we have a network, and so now we're kind of interested, how is this network organized? So what we did is we used resting state data from two data sets to make sure that our results replicate. And we calculated node-to-node functional connectivity, as well as node-to-voxel functional connectivity. So here, that is, I'm talking about those nodes that we've extracted from the meta-analysis. Okay, so why did we do this? Because we wanted to do two complementary analyses here. So one local, using the node-to-node functional connectivity to identify the communities in this network of regions. And as well as a more global analysis looking at how the regions in these communities then, if they relate similarly to the rest of the brain. So here we calculate the similarity between the siege to voxel maps and used PCA to reduce the dimensionality. Okay, so what have we found? Well, first of all, you might notice that the first community of regions here is actually the same regions of the delay consequence sensitivity. So these all clustered together, which kind of nicely recapitulates the findings of the meta-analysis. We find this very similar results for the global analysis, with most of these regions also relating similarly to the rest of the brain. While the other regions of the response inhibition network have fractured into three communities, one being composed of regions that you might call the salience network, those being the ones in the red, so that's anterior insula here and anterior mid-cingulate. The second community here was composed of mostly frontoparietal regions, and the last community being composed of regions that are mostly located around the temporoparietal junction. Again, we find complementary results on the gradient decomposition. Okay, so now to kind of come full circle, we were interested if the community organization actually relates to impulsivity on a molecular level. The reason being that a lot of theories of impulsivity actually talk about neurotransmitters as being kind of inherent to impulsivity, and that being, for example, norepinephrine in psychostimulant medication for ADHD, serotonin in theories of aggression, and dopamine in reward. So what we did is we investigated PET maps of exactly these three receptors that I just mentioned, that's norepinephrine, serotonin, and dopamine, and correlated these with the integration in the functional network, that we have here. So what have we found is that integration actually only correlated with the serotonin 5-HT1A receptor. I will note that this is in both data sets, otherwise I wouldn't be showing this to you. And we checked for significance using a spatial permutation. So here I just took 1,000 random networks, extracted the PET values from these and correlated them with the integration as well. Okay, so with that I will wrap up. So what we found are two non-overlapping meta-analytical networks that fracture into 4 functional subsystems that nevertheless still recapitulate this dimensional structure we find on the meta-analysis. Our kind of preliminary or more explorative research, results suggest that a serotonergic modulation of behavior might be related to integration in this network. And so our findings kind of recapitulate the insights from behavioral research that impulsivity might be a multidimensional construct, as well as here we observe that on the neural level as well. And with that, I would like to thank everyone for your attention. And my poster number is over there. I'll be there during the poster reception and also tomorrow during the first block. I'll be more than happy to talk to you. Come say hi.
Very nice, thank you. We have a few questions. One is, have you also analyzed top signal and go-no-go separately? Some literature shows inhibition mechanism in these two tasks to differ.
Yeah, that's a very good point. So we didn't do that here because we kind of assumed that if there is some aspect of inhibition that is related to impulsivity, it should in theory be kind of common across these two tasks. But of course, yeah, it's a good point. There might be kind of specific differences in those two tasks, of course.
Thank you. Given your results, would you anticipate a correlation between impulsivity and decreased interoceptive abilities?
To be honest, I'm not quite sure what's meant here by interoceptive ability. Can someone clarify?
Perhaps the presenter might want to clarify. Beautiful. Here we are. At microphone one.
Yes, it works. Hi. No, yeah, because I was thinking about your results and I've seen the nice correlation between your construct of impulsivity that you measured and the silence network. Mm-hmm. And the insula is part of the silence network, and it's been demonstrated that it is involved in the updating of bodily related signals. So I was thinking maybe there could be a correlation between the abilities of processing and be aware of one's own bodily signals and the impulsivity in the response. Or
yeah, okay, so that's an interesting question. I will actually use the first, maybe I'll think about the first talk we heard today, well, in the session, there seems to be quite a kind of a separation, right? There's some domain general and some specific, and I would like to think that the one we find here is maybe more related to the cognitive kind of processes that anterior insula might be related to rather than the interoceptive, but difficult to say.
Yeah, of course. It was just at a speculation level.
Yeah. I think the anterior insula is one of those funny regions that appears to kind of come up everywhere, and so yeah, I don't know. I can't really say if
but there's probably something in the literature. Maybe someone knows about it. But thank you.
Thanks.
Well, let's all thank Martin for that very stimulating presentation. And let's thank everybody who presented today. And I wish you a lovely evening and see you tomorrow.